This is the second segment of lecture number 5 in the course ME 760 at the University of Waterloo. We're going to focus in this segment on media concentration calculations. Although I will not present each one of the derivations, you can look at in detail at the calculations and how we got to these numbers in the Human Health Risk Assessment Protocol from the US EPA. Media concentration, we'll start with the soil concentration. Once we emit the COPC, the chemical of potential concern, either through stacks or mobile sources, these go into vapor phase and particle bound phase. They deposit to soils, the particle deposit to soils, gonna go on the soil, there will be losses. There will be accumulation and losses. And the type of losses we're going to have is leaching, erosion, and runoff, and degradation, both biotic and abiotic. At the end, we see how much stays in the soil. It tends to accumulate until it goes into a balance, losing as much as it gains, and it no longer grows. We will see this in the Python code I will present for lecture number 5. This is a more detailed view of what we mean by soil losses. Erosion, there are certain chemicals that will bind so tightly to the grain of soil that the only way to lose that COPC is by losing those grains of soil through erosion. Leaching will have water running through the soil and washing the COPC out of the soil. Runoff is a type of loss over impermeable surfaces, and this is mostly paved roads and roofs on buildings. When it rains, it will wash those pollutants from the pavements. For example, volatilization, the name says it all. Some of the compounds that deposit on soils will volatilize and it gets away from the soil. And the degradation, it will be both biotic, bacteria eating those COPCs, and abiotic, just by common oxidation of the COPC. This is the Python code that we will see. It's related to how to compute these equations. And we went through exponential type equations, and as you see here, we have a constant and we have the losses based on exponential factors. We will discuss this further in the Python code. Soil depth, it's very important because if you have fields, there is no agricultural, no tilling of the soil, then we consider the soil depth to be 1 centimeter. If there is any agricultural activity, we will consider it to be the depth 20 centimeters, that we will have the pollutants. As we till the soils, we inject the pollutants to 20 centimeters into the soil. Water body concentration. As you can see here from the graph, runoff from the surfaces that do not absorb those pollutants, the water will wash from the surfaces and bring it here. Soil erosion, we get again losses from the soil, will go into the water body. Direct particle deposition, direct vapor transfer, and volatilization from the water body back to the air. We also have an important loss called benthic burial. As we bring soil erosion, it will accumulate layers of soil particles at the bottom of the lake, and it will then lose that concentration, will not be accessible to the water body anymore. There we go again. These are the variables we're going to use in the coming equations. Total deposition, L, all of them will have L. Deposition, diffusion, runoff impervious, runoff pervious surfaces, just R. Soil erosion, internal transfer. The diffusion to water body, the LDIF, computed by this, we also have that in the Python code. Produce concentration, direct deposition of particles, as you can see here, and vapors. Here, and root uptake. As the soil gets contaminated, the roots will absorb COPCs and inject in the plant tissue. Produce concentration, this is how we compute this. Beef and dairy, we'll have wet and dry deposition of particles and vapor to plants. Then we get forage and silage concentration. We also have root uptake and our friend soil concentration, transferring this to root. Once we get those plants, we are stored here. Now we could have grain concentration directly from here, because grain concentration, the grains are protected from the direct deposition over the plants, but the grass will not have that protection. When we store the grass, for example, it will contain on the surface of the leaves concentration of pollutants. And then once we have this, we will compute the concentration in beef and dairy products. Remember that animals, as they graze, they ingest a little bit of soil, so we must account for this ingestion. This is how we compute the beef and dairy concentration. This is for the A beef, and you can see here we have soil bioavailability factor. For example, cow eats a little bit of soil. Not all the COPC in the soil will be absorbed by the animal. For concentration, very similar, wet and dry deposition of particle, vapor transfer, silage. We also have here for the grain production, soil concentration affects everybody, and we get the concentration in the pork tissue. This is how we compute the pork concentration. Poultry concentration, we will consider that chickens need to ingest a little bit of soil for their digestion. All the birds are like this. It will have soil plus the grain concentration, and we consider this to be free-range chicken, by the way. This is how we compute the chicken concentration and the egg concentration, and the only difference is here. The biotransfer factor for chicken, biotransfer factor for eggs. Fish concentration, we need to get the water body concentration, and we already saw how it comes to happen. And once we have the water concentration, we need to split this into dissolve phase. Some chemicals will dissolve in water, some will not. Some will be over suspended solid. We call that TSS, total suspended solid. It will sorb to those total suspended solid. And we need to compute the concentration based on the dissolved, total water column, and bed sediment. This is how we compute fish concentration.